I guess so. Okay, cool. Right, hi everybody. Thanks for coming to the last talk of the day. Today we're going to be. Yeah, that's good. Okay, yeah. So we're joined by. So today the last talk's on Gaussian process, multiple output Gaussian processes, and we're joined by Felipe Tobar, who is a lecturer at the University of Chile. Who lectures for the Initiative for Data and AI. His interests are in the areas of statistical machine learning and signal processing, sort of working on the sort of things that people have been talking about already in the Gaussian process summer school around inference. And yeah, hopefully he'll be able to cover more of this sort of problem in his talk. And later, and maybe later, if you have a moment to join the Slack, maybe tomorrow. I don't know if people might have direct questions.
Sure, yeah.
Yeah, it'd be great. And anyway, I won't waste any more time. Yeah, feel free to get started. How do you want people to ask questions? Are you okay? Shall I just interrupt you at appropriate times and I'll keep an eye on the Q&A?
Maybe every 5 slides or so I can look at the chat and answer the questions.
Cool, that sounds great. Yeah, fantastic. Cool, thanks very much.
Good. So here it is. Yes. Okay, good. Well, thanks very much for inviting me to the summer school. Thanks to the organizers, and thanks everyone for being here as well. I'm going to talk about multi-output Gaussian processes. This is going to be a crash course in 1 hour. And I'd like to start saying how great is that we're so far away. We're almost 12,000 kilometers away, and still we're sharing this summer school, right? I'm pretty sure there are people all over the world connecting to this streaming. And I am based in Chile, at the University of Chile, as you can see here. But at the moment, I'm not in Santiago. I am a little bit far north. So I'm giving the tutorial with this view. I thought I could share this view with you, even though it's a little bit cloudy, as you can see. So this talk is going to be, as I said, a crash course on multi-output Gaussian processes, MOGPs, from now on. And I'm going to start motivating the need for multivariate processing, right? For considering all channels together rather than every channel independently. We're going to define the MOGP, and the main focus of the talk is going to be on the covariance design, which is the first main challenge of MOGPs. Then we're going to see a few examples, illustrations, and a short demo. We are creating a toolbox for MOGPs, which is available. Still lots of things to do to incorporate, but I'm going to show what we have in that respect. I'd like to start with a personal note on how I ended up working with GPs. In our community, one of the rich things is the diversity of the community in terms of academic backgrounds. We have people coming from physics, maths, neuroscience, computer science, engineering, and there are many different paths. In particular, I started as an electrical engineer. I got my MSc and my Bachelor of Science, and also my PhD in electrical engineering. I worked with particle filters in my Master of Science degree, where I was introduced to Bayesian analysis. Then I worked with kernel methods applied to signal processing, and then uniting particle filters, Bayesian analysis, and kernel methods, the jump to Gaussian processes was very natural, right? Which I did in my postdoc. I focused entirely on GPs. And then after that, I became more independent as a research fellow in a department of mathematics. And then I started applying these ideas to spectrum estimation, so how a signal oscillates in time. And I think there's a fertile ground there for incorporating ideas from spectral estimation to kernel design, and also to using GPs for spectral analysis, right? And at the moment, I'm currently a lecturer, and in addition to GPs, I'm working on things like optimal transport, which is very preliminary to me, but it's something really nice. So to motivate the need for multivariate processing, I want to mention 4 things. The first one, or 3 things actually. The first one is that there exist shared sources of uncertainty. For example, in neuroscience, in electroencephalography. We have these sensors, they're called electrodes, and they're recording neural activity, and each electrode is measuring the electrical activity of one region of the skull. And in that region, there's a population of loads of neurons that are firing together. And by adding these firings at different times, we see a signal that maybe based on the central limit theorem, we could say is Gaussian, because it's a summation of a bunch of different responses, right? But the electrode that is besides the first electrode that I mentioned is also sensing a region which incorporates some of the same neurons. So there's, of course, information shared among different electrodes, and therefore they're going to be coupled. Another scenario where the same phenomena occurs is the financial market. So here we see different exchange rates, but the same happens with stock prices, that they are a response of the state in which the market is, which in turn might be driven there by political announcements, climate events, and social events, and different things, right? And of course, this is, in that sense, the market and the society are alive, and they react to different stimuli, and they respond in different things that we measure, for example, the stock prices. Another reason is that sometimes in some applications, what it is really of interest is to analyze the relationship between or across different measurements. So for example, here we have a huge truck. This is a 20-cylinder, 4,000 HP. It's called the Caterpillar 797, which is this truck that carries the load from a mine. Okay, and as you can see, it's gigantic. So this is a big truck, right? And it's like half the size of the tire. And there's lots of technology in these vehicles, right? Pressure sensors, torque sensor, payload sensor, and so on. And it is different, the measurement that these sensors acquire in different conditions of operations for this machine. So for example, if you are applying certain torque to the operation of the machine, and the machine is unloaded, is different if the machine is loaded, and different materials. And by neglecting the relationship between what the group of sensors is saying, you might end up with things like this, which is a truck, this gigantic truck that went back to drop the load, and it fell into a hole, basically. Of course, as you can imagine, it's nearly impossible to lift it from there, right? So basically, you can develop a multivariate analysis system, and you can measure and analyze all the recordings like in this system here. The third reason that I'd like to mention that motivates the needs for multivariate processing is that not when you have multiple channels, a multiple channel phenomenon, not all channels are observed at the same times. And an example of this is Astroinformatics. So this picture at the left is a galaxy. Okay, so this is the galaxy, and this blue-white dot is a supernova. So it's a star that just died. And when the star dies, so when we have a supernova, the explosion emits a light that has loads of information about the contents of the star, of the dying star. And this luminosity is observed from different, well, of course, from the surface of the Earth, with different devices and different telescopes. And because the Earth is rotating, different telescopes observe the light at different times. And each well, not each telescope, but different telescope will observe different parts of this signal, right? Because it is light, but the light is observed at different bands. So if you want, at different colors. And what we can see in the image at the right is at which times each color of the light was observed. And then the pattern of the light curve, which is the amount of flux luminosity that comes to the telescope, needs to be reconstructed for all these measurements, right? So let's go into what this talk is about with that motivation. By now, you already know what a Gaussian process is. Okay, so it is a GP is a stochastic process such that this condition, right? A finite collection of values follows a multivariate normal distribution. And we have this notation at the bottom here. So now the question is, how can we extend this definition to the multi-output Gaussian process? And it is very straightforward, right? We only need to replace the word here values by vectors, right? So it looks like this. A definition is and the definition of an MOGP is a vector-valued stochastic process such that any finite collection of vectors now follow a multivariate distribution. Okay, so it looks like this. Right? This looks like a cake, actually. However, the fact that we say that at each time that we see that we're going to have a vector now because we have multiple channels. But recall that the Gaussians have a very specific property, which is closure under marginalization. So if all these red points, sorry, all the pink bars are jointly Gaussian, then each subset of these points is also jointly Gaussian, right? Like this. So perhaps a more accurate definition is that if we have a multivariate or a vector-valued stochastic process, and then we perform any choice of points at any time and any channel, those points follow a multivariate normal distribution. So that is a little bit more flexible than the first one, but it is implied by the first definition anyways. I'm going to look at the chat now to see if there's something I should answer. There is something there. Yes. No. Okay. So let's continue. Now, how do we specify the covariance of an MOGP? There are two ways of understanding it. So I am putting here two definitions to see which one is easier to understand for everyone, because maybe at the beginning we're talking about an infinite dimensional process, and then we marginalize, we get the gram matrix, right? But then the gram matrix is multi-channel, so sometimes one might be a little bit confused with the dimensions of the objects we are working with. So let's revisit this definition. So first, a little bit of notation. The input space is going to be called calligraphic X, which I'm going to just read as X. This is usually R, or in general, Rn. So the n-dimensional vector space of real entries, right? Our GP is going to be denoted by F, which is a collection of scalar valued GPs, M channels. We're going to denote it MOGP mu K, okay? So the MOGP is specified by the covariance function, which is a four-way array. So this is the important thing, right? So the covariance now is a function from a four-varied space to R, which looks like this. We have two inputs that are the channel, which is a discrete variable. This is a typo here. This N should be an M, okay? So the I input, the J input, and then the input space inputs. Okay, I'm calling them X and X prime. So for each pair of values, coordinate I of the function F at X and coordinate J of the function F at X prime, we have the covariance defined in this way, which is the standard GP covariance practice. But there's an alternative definition, because we can see a four-way array, a function that starts in 4 dimensions and ends in 1 dimension, as a function that starts only in 2 dimensions, but ends in 2 dimensions as well. So this is a slightly different definition, and that's why I use a different symbol for K. This is calligraphic K. So the kernel can also be understood as a matrix-valued function that has a starting set, which is only X cross X, okay, not different from the first definition, but it arrives at a space of matrices, okay, and has the conditions of symmetry and positive definiteness. So basically, we could see the covariance of an MOGP as a function that goes from a space of 4 inputs to a single number, or a function that goes from a space of two inputs, which is the different timestamps, right? And at each two timestamps gives us a full matrix. And to understand that, I'm going to go back 2 slides to this figure. So the second definition is saying, sorry, I'm going to start with reference to the first definition. The first definition is based on this figure, which basically says, take any pair of points, okay? So say, for example, this one and this one, and each pair of points is defined by a channel and a timestamp. So this is second channel and this timestamp, whereas this red point is third channel, this timestamp. So we have four coordinates, and then with those four coordinates, the kernel will define the covariance between those 2 points. Now, with the second definition, we're saying only give me the 2 timestamps. So say, for example, x3 and x4, and the kernel is going to give the covariance matrix related by these 2 entire vectors. That is a notational difference. Okay. Okay, let's continue. So as this object is a 4-dimensional array, we cannot possibly show it here, right? Because we are now in this virtual summer school, we're living in 2 dimensions. So we could visualize things in 2 dimensions and maybe with a little bit of perspective in 3 dimensions, but not in 4 dimensions. But what we can do is slicing, okay? Because even though we have 4 dimensions, 2 of them are discrete. So we can cut or slice this object and show all particular cases for each dimension. And the continuous dimensions remain on our screen, basically. So this is what's happening here. I applied slicing to the covariance matrix, and I am, in a way, concatenating 1 discrete and 1 continuous dimension. This is what we're seeing here. So we have channel 1, channel 2, channel 3, and so on until channel M. And if we go downwards, it's the same thing, channel 1, channel 2, channel 3, until channel M. And at each pair ij, so channel I versus channel j, I plot the covariance, which is a continuous object in this position, right? So this is one way of visualizing it. Now, this is nice for visualization, and in the example that I'm going to show, we're going to see a real example of this covariance. This is just an illustration. But the problem with this formulation is that it doesn't allow for parametrizing the covariance, right? I cannot place a function over this entire blanket of covariances because there are discontinuities, right? Not because I'm plotting this point at the border of K22 and this point at the border of K23. Those points have nothing to do with one another. They correspond to different channels and different times. So this visualization might be a little bit tricky if we want to parameterize the covariance, right? But what is nice about this representation is that this is a covariance function of another thing. This is actually a true of covariance function, because if we take all these points and we concatenate them in one vector, so say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then continue with that vector and take the points in the second function and then concatenate a big vector of all these red points, and I want to show the covariance function of that construction, that covariance function is going to be this thing. Okay.
Cool. Somebody quickly asked, could you just move the box? I think it hides a couple of the slides.
Oh, okay. This one, right?
Yeah, like we can't see it. It just looks like a gray box. Hey, sorry, thank you.
Okay, no, so I want to have it there in case there were questions, but just if you want to help me with that, that would be fine.
Yeah, no, I'm happy to.
Good. Okay, so one way of reducing the dimensionality is to assume stationarity. Because if we assume stationarity, we no longer have 4 dimensions because the temporal dimensions collapse into 1. Because we don't need to have both inputs, only the difference between inputs. And of course, we know that for covariance to be stationary, we have this condition, which in the multi-output Gaussian process case turns into the condition for all possible pairs, and we have something like this. This might not sound like much, so we went from 4 dimensions to 3 dimensions, but it's going to be critical for the construction of the kernels, because now the kernels are going to admit a Fourier representation, as we're going to see in a few slides. And now we have this representation in 3 dimensions. And let's take a minute to do a few observations of this representation. First, if we take slices like this, so slices parallel to the plane of the screen, we have the covariance function at different times, which means the covariance function between vector observations, so all the channels, at different lags. That's the first thing. The second thing that we can see is that if we look at the diagonal and look into the screen, these are called fibers. So we have slices and fibers going through the screen. The ones in the diagonal are going to be positive definite because they are the kernels of each channel. And in a multi-output GP, each channel is in particular a scalar value GP. And the covariances of those scalar value GPs are encoded in the diagonal of this cube. Now, the interesting thing, which is might sound counterintuitive at the beginning, is that the off-diagonal fibers need not be positive definite. Actually, they don't need to be anything. The covariance of 2 points at different channels and different times marginally, so this covariance has no restriction whatsoever. The only restriction is in the group of covariances. Okay, of course, when we set the marginal covariance and covariances among other channels, the particular covariance between a pair of channels is constrained. But if we didn't set any other values, the off-diagonal functions in this cube could be anything. And that is a double-edged sword, right? Because the objects that we can create, we would like them to be very, very flexible, but still there are some requirements they need to fulfill, and they're non-trivial requirements, as we will see soon. So how do we design the kernel? As I said, this is a trade-off between the aim of having very, very expressive functions, the fact that hopefully all the structure is discovered, so we want to be agnostic about the covariance design, and also that the kernel parameterization is constrained in an intuitive way. In an intuitive way, I mean, someone might disagree with the unintuitive way, right? Because it's very intuitive. The matrix is to be positive definite, positive semi-definite. But if you try to understand what that restriction means in the parameters, it's unintuitive, right? So if we search the hyperparameter space for a certain parametric form of a kernel, the space where the valid parameters lie, that is the unintuitive thing. So let's start with something simple rather than setting the ambitious aim of constructing a parametric form. Let's do something that is much simple, which is just mixing GPs. So let's take, in this case, 6, but let's say n GPs that are independent and they have a specific kernel. And let's mix them together, like in this linear 2-layer neural net. So each GP is entering the input neuron and then is being propagated to all the output neurons. So we have 6 channels for input and 5 channels for outputs. They're all mixed together with weights denoted theta ij, where theta ij connects the input I with the output j. And this construction is going to give us a certain multi-output covariance, which is going to be a consequence of this construction, right? So we're bypassing the direct parameterization of the covariance by seeing what is the result of this construction. And recall the notation. So theta are the weights, G is the input GP, and F is the output GP. G is just a collection of independent GPs. And let's see the mean and the variance of this construction, because it's a Gaussian process, so we only need the mean and the covariance. Unsurprisingly, the mean is just the matrix of weight times the original means, right? And the variance, everything is linear, so we can decompose and compute explicitly, and we have this form. So basically, the output the covariance of the output process of this MOGP is a summation of all the covariances of the input processes, but weighted by these vectors, right? Theta Q. And theta Q is the qth column of the Q matrix, right? The weights, which corresponds to all the weights that come from input Q. So basically, take an input, register all the weights coming of the signals coming from the from that input neuron, and then construct this kernel and do the outer product of this kernel. This is positive definite, right? And then multiply that for the kernel, and then sum for all Q, for all the input processes, right? This is a general form, but there are specific works that have focused on special instances of this construction. The first one is the famous linear model of corrosionalization, where the assumption is that there are groups of input Gaussian processes that even though they're all independent, there are groups that have the same covariance. So with that assumption, the form is a little bit different. So we're grouping some of these channels. We're assuming some of these channels have the same covariance, so they group them in the summation to form this term here, which is called the corrosionalization matrices. There's another model which is called the intrinsic model of corrosionalization, which assumes that we have Q equals 1. So basically, there's one source of uncertainty generating all the outputs. Well, not the one. There might be more than one, but they all have the same kernel. And then there's a semi-parametric latent factor model, which poses no constraint on the weights. Right? If you want to look at very, very nice review of these things, of course, you are recommended to go to Mauricio's review of kernel for vector valued functions, which is a very nice paper. It just doesn't age. I like it. Now, what is one drawback of the above construction? The main drawback, I'd say, is that the construction is a photograph, it's instantaneous, right? Because you have a set of incoming Gaussian processes and you mix them without having any sort of memory, right? So you take a photo and then mix that, right? And as a consequence, the multi-output covariance kxx prime only depends on the covariances at those times. And this construction results in a separable kernel, which is this expression here, and basically says that all the temporal structure of the process is inherited directly from the temporal structure of the input process, and the mixture, the only thing that adds is channel-wise structure, right? But we want to mix processes and introduce temporal dependencies as well, in addition to the temporal dependencies that the original processes might have. And to do that, we can do the following observations. What we're doing is this figure at the left. So between two neurons, input and output neuron, we have that the Gaussian process is amplified by a certain scalar value, right? So this is the input, the I input, I amplified by this weight, the theta ji, and this is the component that enters the output neuron, right? But if we recall that G is a GP, the linear operators for GP, so for functions, is much more expressive than a scalar, right? It's something like this. Is basically a kernel. It's a two-valued function. So rather than taking just point-wise amplification, we can take the entire GP and rotated linearly, right, in the space of functions. And this is what this is doing. Actually, this construction is a particular case when in the construction on the right, the function theta ji is a Dirac delta. Okay, and this is called a convolution. And some of you might be familiar with the term moving average. Basically, the GP is going through the neuron, and the neuron is applying a filter and mixing all the values together in time. That's what's happening. That's called a convolution. With that convolution, the kernel looks fairly similar to the one we constructed here. Okay, I went back two slides. But rather than this linear form here, we have linear forms, but integrated over the domain of these weights. Now, these are input-dependent weights. Okay. There are two subtleties. The first one is that notice that we have now a kernel which is defined sometimes in the entire line, like the square exponential. So it's defined in the real line. It has infinite support, and this window might also have infinite support, or maybe it doesn't have any infinite support. But the things that we need to guarantee is that this convolution is finite, because if we're multiplying two objects that go from minus infinity to infinity, we want to make sure that that integral is not infinity. And for that, there are certain conditions on which windows we can operate here. Basically, you need it to be square integrable. And also, there's something interesting, that this model might be non-causal. That means that to yield the output of the system at time t, you're using data at time t prime greater than t. So you might be using future values of a process to construct current values of the process. In practice, it's in general no problem, but it is a nice phenomenon to analyze from causality perspective. Okay, so which models are built on this concept now? There are many models built on this assumption, but I'd like to mention a few of them. The first one is when the driving process is white noise. Now that through the mixing, we're able to include temporal dependencies, maybe the input processes need no temporal dependence originally, because all temporal dependence might be included through the mixing. So we might consider input processes that are white noise. And that looks something like this. Okay, so you have a latent source which is white noise, and then a convolution filter, or a moving window, or a kernel filter, or however you want to call it. And the convolution between this window and the latent source will look something like this. So basically what is happening is that in each blue point, you're placing one of these windows there and then summing them all together. That's what's happening there. Of course, the kernel of this construction is the convolution filter times itself, which is what we have here. So we have the 2 times integral. This is the convolution filter. This is another convolution filter, and this is the kernel. But in the case of the of the white noise, this kernel is a Dirac. So the Dirac disappears, one integral disappears, and you get basically the convolution of the filter with itself, which in this particular illustration looks like this. There are other cases where the kernel of the input process and the window are square exponential. And in those cases, this integral can be computed analytically, because the integral of Gaussians against Gaussians is also Gaussian. And another case is where the filter, which is what gives all the expressivity to the model, is another GP, which is actually this figure. So you generate white noise, you draw a GP from another square exponential GP or something like that, and then you convolve. And theoretically, this is a non-parametric kernel, right? Let's continue. So far, we've seen the construction of covariance functions via, if you want to call it like that, induction. So you take some GPs, you mix them in a way, either instantaneously or dynamically, and you get the covariance function as a consequence of that. But what we're going to do now is to design the covariance function directly, right? Well, almost directly. We're going to parameterize them in another domain. So basically what we'd like to do is to find a representation of the matrix, sorry, of the kernel in certain space where it is unconstrained. So basically we have a generative model that takes elements in this space, and each element is converted into a covariance function. And one of the requirements I'm going to have for this procedure is that the objects in this representation space are unconstrained. So I can choose any of them. And it is only the mapping that's going to give me for any object in the representation space a covariance metric is this mapping, which makes sure that the output is a valid multi-output covariance matrix. That might sound a little bit disconnected from a kernel design, but that is basically the concept that we use for the spectral mixer kernel. So in the spectral mixer kernel, this is an example for the scalar GPs, not for multi-output GP. You have a set of Gaussians in the frequency space, right? And the Gaussians here are denoted in blue, orange, green, and red. And then you sum them all, and you apply the anti-Fourier transform and go back to the covariance space. Now, there's a theorem that's called the Bochner Theorem, or equivalently the Wiener-Kingen theorem, that says that any kernel or basically any positive definite function has a representation in the Fourier space, and the only condition for that representation is positivity or non-negativity, actually. So any function that I put in the frequency space that is non-negative, when I apply the anti-Fourier transform, I'm going to have a positive definite function. That is something like something like what we're looking for. And we're going to do this thing, but for multi-output GPs. And for multi-output GPs, there's Bochner theorem has an extension, which is called the Chrome Theorem, which is this one, which is exactly the same thing. I'm not going to go through the statement of the theorem, but basically says that for any family of covariance functions, there is a family of Fourier representations that have a certain requirements. Now, there's still a requirement for positive definiteness, but informally, that requirements runs over fewer dimensions. What does that mean? The original object we want to construct is this one at the left, which is the covariance for what is the covariance? It's a 3D covariance, basically, because we have the channel dimension, and time dimension. And any choice of points need to be positive definite. So if I have, if I choose 2 channels or 3 channels here, 2 there, and I have a set of points in time, and I marginalize this cube, I have a little cube that has to be positive definite. And if I choose differently, that has to be positive definite, and so on. This is what I meant. It was very hard to achieve. But with Chrome Theorem, which is the multivariate version of Bochner Theorem, basically says that design a cube like this, and the only condition you need to fulfill is the following. Every time you take a slice, so a slice parallel to the screen, the corresponding matrix, like this one here, has to be matrix positive definite. Okay, so it's a positive definiteness requirement in the discrete dimension, not in the continuous dimension, which is the complicated one. So let's recall something. We started with a 4D cube, a 4D array, so a four-way array. We assume stationarity. Now we end up with a 3-dimensional array. Now, from the 3-dimensional array, we applied Chrome Theorem, and now only need to construct a 2-dimensional array, which is one slice of this cube, right? And why only a 2-dimensional array? Because unlike time, where a Gaussian process needs to covariate more with its value, time 0, than other times, right? Of course, a value of the Gaussian process cannot covary more with another value of the same process rather than itself, right? But in frequency, that condition doesn't exist. At one frequency, so at one oscillation mode, a time series doesn't need to be more correlated than another frequency. That condition in frequency doesn't exist and is embedded when we apply the anti-Fourier transform. So we went from 4-dimension stationarity, 3-dimension Chrome Theorem, 2-dimension, and now we only need to build a 2-dimension matrix parameterized by omega in this case, and to construct a positive definite matrix, we use Cholesky. That's simple. So recall 4 dimensions, stationarity, 3 dimensions, Chrome Theorem, 2 dimensions, Cholesky, 1 dimension. And now we only need to build things in 1 dimension and then apply Cholesky anti-Fourier transform, and then we have the 3-dimensional object we were looking for. One way, this is the 1-dimensional object. So again, 3-dimension K, 2-dimension S, 1-dimension R, where R is R transpose R. And of course, R is a free choice. So we're going to choose a square exponential. But it's a square exponential in the complex space. So it's a square exponential that is a Gaussian that inside has a degree 2 polynomial, okay, a quadratic polynomial which has complex coefficients, right? So it's a Gaussian, but in the complex plane. And it has a few parameters, looks like this. So the cross covariances look like this, and the cross spectral density looks like this. Blue for real part, green for imaginary part. And the key thing of this model, which is called the multi-output spectral mixture, which is here, is that it has some delay parameters. So you can model how delayed are different channels among one another. Okay. This includes other models are particular instances. So for example, the cross spectral mixture that you might have heard of. The previous models, they're also modeled by the multi-output spectral mixture by setting the angle in 0. So basically this R function in the origin and so on. And this is an illustration of how it works. This is a very simple but nice example. This is a 3-dimensional multi-output GP, so 3 channels. And the first channel is just a draw from a spectral mixture. The second channel is a derivative of that signal, the numerical derivative. And the third channel is a delayed version. Okay, so it's the same first channel, but delayed a little bit. And we have data from the first channel, which the data is plotted in green. I hope you can see it. And for the second and third channels, we have data only for the first half of the experiment. The true lines are plotted in dashed line. And the multi-output spectral mixture predictions are in color, so blue, red, and yellow. And of course, the model also learns the kernels, right? So the reference kernel, the derivative kernel, the kernel between the reference and the derivative, and so on. It works very well. Of course, the model is well specified here because the data came from the model. But it's nice to know how well it works. Now onto a few real-world applications. We have applied the multi-output spectral mixture on financial data. So we can see exchange rates here with respect to the dollar, the euro, Canadian dollar, Japanese yen, the British pound, and so on. And we have the points denote the observations, and the pink bands denote sensor data. So we want to perform imputation in these lines, in these bands. And this is the collapsed gram matrix, where we can see that, for example, the Hong Kong dollar is negatively correlated with the euro, the Australian dollar is correlated with the Canadian dollar, and so on. Okay. Another example is EEG, which is far more complicated. We've been struggling a lot to get this working, but we've obtained very promising results. This is basically the same experiment as we did with the finance example. We have 16 channels. This is neonatal EEG. We have randomly removed data, and also some of these electrodes have 1/3 of the entire recording completely deleted. This is to simulate sensor failure. So you have an electrode in EEG that falls. We would like to see if the method can reconstruct them from the neighboring nodes. And the experiments are, as I said, promising, and we learn a few things. So for example, sensors or electrodes C3, P3, T5, which are P3, C3, so this one, And where is the 5 in this one? So these 3 should be recovered. So the recovery in these 3 electrodes, which are the ones that have censored the last third, should be recovered less accurately than the rest, because these form a cluster and then they are left without neighboring nodes. Okay, rather than F4, for example, which F4 is, where is F4? Is here, where the prediction is much better, because F4 is surrounded by nodes that have complete data. We developed as I said, a toolbox that is called the MOGPTK, the Multi-Output Gaussian Process Toolbox, that is always under development. I'm going to briefly show where it is. So you can go to the project website. Is GitHub Games with Chile MOGPTK, and we've worked on having the documentation up and running. There's instruction for installation and upgrade if you installed it already, and there's loads of tutorials and examples. So if you navigate to we have 6 tutorials, examples with the standard data, the airline passenger data set, the Mauna Loa experiment, very, very famous and maybe known by you all already. The one that I show with the gold oil and all other financial indicators, and the famous BrambleMet data set, which I have here. Okay, so this is an example with the BrambleMet water level example. So I'm gonna guide you very quickly. First, we load the data. The toolbox is very well integrated with pandas, so for visualization or removing data or pre-processing data. Also, the main aim of this toolbox was to facilitate the use of MOGPs by data scientists and people that are not very deeply working on GPs, because training these models is very, very difficult, especially the models that are based on spectral kernels, very hard to train. So this framework provides initialization strategies. So first it runs some spectral estimation techniques to find the peaks of the power spectral density, and with that in mind, initializes the parameters and so on. So this is the example we created for this notebook. These are the signals, right? So the Bramble, Cambermet, Chimet, and Soddenmet. We see the spectrum, the power spectral density as a initialization strategy, identify the peaks, the widths, and so on, set up the parameters, and we can see here we have MOSOM kernel with 4 channels, 2 mixtures, 646 training points, 48 parameters. We have the initial loss. This is training, blah, 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 all the models. And results look like this. This data is known to be very, very highly correlated, so an MOGP does very well. And we can see how the predictions are shown for MOSOM, for the spectral mixer linear model of corrosionalization, for the convolution model, and for the cross-spectral mixer model. And if we want to see indicators, the MOSOM does better than the rest, because the MOSOM is the multi-output spectral mixture is a case that is more general than the other kernels. It collapses to the other kernels when constrained. But sometimes things don't work. For example, in this example, okay, this is an example that we run only for this tutorial. These are, well, the same thing. We load the data set, and we loaded the data set from different sources. So oil price, gold price, the NASDAQ indicator, and the USD indicator. We see the data. Okay, this is the data we have. Points denote observations that are going to be used. Dashed line denotes observations that are held for training and are only used for the validation. We removed a region of the USD index to see if we can recover it. When we removed an entire range, it's denoted like this by the toolbox, and when we delete data, like data points, it's not denoted in red. Basically, we have a few functions here This function is called channel remove randomly. Basically, remove 60% of the data in that channel and so on. Or you can remove a range and so on. Same thing again. We're going to run spectral estimation first to initialize hyperparameters. Here you can see how the parameters are initialized. Only half a second is very fast. The initialization is very fast. But then the Moson.train, which trains the entire model, it takes 3 minutes. You have to determine the learning rate, the error criteria, and so on, the number of iterations. For example, here, using the Moson model in 4 channels, 6 mixture of the spectral mixture, 145 parameters, and so on. With the Moson dot check and plot, you can see the covariance matrix shown in different formats. As the figure I showed you before in the presentation. So it looks like this. These are all the covariance functions of the MOGP, right? The diagonal are the autocovariances and the rest are the cross covariances. Of course, for example, this one and this one are the same flipped. Okay. But now, as we can see, we have this problem here. Okay. So one might argue, excuse me, that this would have been better predicted without the other channels, because this escaped here a little bit, and there is no evidence in the same channel that indicates that explosion here. But my conjecture for this specific example is this thing here, or this drop here. Okay, so what is happening is that the model is learning a dependent spurious correlation, basically, and that in the literature is called negative transfer of knowledge. So basically, the model, in its aim to be too flexible, it learns particular cases that might not be too accurate in the subtleties in the regions where we have data. So, for example, take this example. Here, this signal is coming down, and this one is coming up, and this one is coming up, and this one is coming up. So one might argue that every time all the signals are coming up, the 4th channel is coming down. And this is a strong jump. And of course, without looking at the parameters, I don't know how much each of the channels weights on the 4th channel. And things like this happen, right? This is referred, as I said, as negative transfer of knowledge. And it's something that we didn't see today, but it's something important nonetheless.
Cool. Can I interrupt for a second? There's a couple of questions about the...
Sure, yes, yes.
Yeah. Oh, there's even more. I hadn't scrolled down. Artem says, could you generalize this approach for multiple types of continuous covariates, such as spatial and temporal?
Yeah, I'm going to attempt to answer these questions now. So yeah, could you generalize this approach for multiple types of continuous covariates? So if you mean by mixing different types of variables to be modeled as the MOGP, yes, of course you can. Sometimes when you want to put everything together, like you said continuous, but sometimes you want to include discrete values as well, the relationship among the channels is much more complicated than just second order. And in those cases, the Gaussian assumption fails much more frequently than in the scalar case. So one, of course, is tempted to include different outputs at the risk of assuming Gaussianity when there's no evidence to assume Gaussianity. One thing we can do, in particular for continuous variables, but also for discrete ones, is to stack the multivariate object with nonlinear transformations of the data so that you ensure Gaussianity. So basically, your generative model will be an MOGP, and in each channel, a nonlinear likelihood or a non-Gaussian likelihood. That would be the way I do it. Shall I go through the questions?
Yeah, sure. Go ahead. Yeah, I think the next two are sort of related, maybe.
Yeah. This toolbook is also working with large data sets. Well, large is relative, but if you mean to ask if we have included any sparse GP modules in the toolbox, not yet. So everything is exact. We're working on incorporating variational inference-based sparsifying techniques to deal with large data set. That is a bottleneck of the toolbox. So this is a very specific question. I have a time series dataset with 145 channels, of which 13 can be measured reliably. Training data can have approximately 1,000 time points. Do these numbers sound feasible for? Oof, no. I'd say no. But that is only motivation for us to keep developing this thing. What I do in that case, I try to run something like PCA first to decrease the number of channels to something more manageable, and then apply a toolbox, this one or other. Nicole Carisi, in cases that we have limited data from experiments of different variation of a system, do you think that such a method is suitable to approximate the response in the areas we lack data? Variation of a system. Yes, of course. So, but the fact that you say experiments of different variations of a system mean that the channel, if I'm understanding correctly, the channels are all the channels are heavily correlated. So sometimes they're so dependent on one another that there's little space for uncertainty, and you might have ill-conditioned matrices, right? So you need to take care of that. But in general, I'd say that is specifically the case that these models target. I think I answered everything. So I have 2 minutes, which is fine. My closing remarks. First, a summary, what we saw. MOGPs are just like GPs, of course, but vector valued. Unsurprising conclusion. The main challenge is the covariance design, but there are other challenges. You pointed out very correctly in the questions, which is the complexity, right? The amount of channels you can deal with and the amount of data points you can deal with. In my opinion, to deal with those cases, you need to perform dimensionality reduction, either before using the MOGP techniques or jointly. So you can also train the dimensionality reduction as a part of the training of the GP. And there are many different kernels, but if you look closely, there are types of kernels, and via hyperparametric restrictions, you can recover one or another. Things we didn't cover because we only had 1 hour are non-Gaussian likelihoods. But of course, we had a very nice talk by Estijon this morning about that. Of course, the same ideas applies, slightly different for the MOGP case. Sparsity, recommended. I'd like to recommend this tutorial, which you can apply. It doesn't talk about MOGP specifically, but the ideas in general and very well explained. Non-stationarity, a hot topic, if you ask me, on MOGPs. There are lots of nice works appearing on how to turn MOGPs non-stationary. And what I mentioned at the last experiment, which is the negative transfer of knowledge, and how via a prior you can reduce the effect of that. I would like to thank my collaborators. Taco was a data scientist at the center where I work, and the rest, all of them have been my MSc students. Half of them graduated, half of them going through it. Yeah. My clock says it's about time to finish.
Cool. Yeah. Thanks very much. That's fantastic. Yeah, I did not know. I think Maurizio had been mentioned your work quite a lot, and I hadn't had a chance to myself to look at it. So that's really appreciated. There's a couple more questions. I could unmute them,
sure.
I guess. Maybe.
I'll go to, yeah. Is there an application of this methodology other than applications with time series? It is a common multi-output GP. How to actually access and evaluate the variance of the prediction from the optimized kernel. Okay. So other than time series, yes, I'd say the most famous application is geostatistics. As you know, GPs in the geostatistics community is called kriging, and multi-output GPs are referred to as co-kriging. And there's a famous dataset which is called the Jura dataset that has different recordings of different concentration of minerals. I think it's copper, cadmium, zinc, something like that. in different regions of Swiss Jura, I think. And the idea is to reconstruct the concentration of one mineral using another mineral. So that is a 2D example. But it becomes even more computationally demanding because you have multiple outputs and now multiple inputs, more parameters to train, which becomes complicated in terms of computational complexity. And then the second question was how to actually access and evaluate the variance of a prediction from the optimized kernel. Well, this is exactly the same as the scalar GP, because remember that a single value, so at any channel and at any time, that random variable marginally is a Gaussian variable. It's a scalar Gaussian variable. So you need to look at the kernel expression and construct the conditional covariance, the posterior variance, and evaluate it via the parametric form that you have chosen. And then Simon Riddle asked, I may have missed it, but what is the current state of the art of the maximum number of channels in models with a reasonable computational cost? I haven't tried in this toolbox more than 25 channels, but the restriction is not in the number of channels per se. The restriction is in the amount of data. So for example, if you have 100 data points per channel, that is equivalent to having 10 times more channels, but only 10 data points per channel. So as I said, maybe the take-home message of the entire talk is that, of course, you have multiple channels and have recordings at each channel. If you take all those observations and forget about the channels and concatenate them, that is a Gaussian process. The thing is that the equivalent covariance function is going to be so complicated because it's going to have discontinuities everywhere that it's impossible to parameterize. But in terms of computational cost, it's exactly the same. Valentin Bellet asks, maybe you already explained it, but how do you choose? But why do you choose not to use LMC? Well, I didn't choose LMC because LMC doesn't model delays among channels. So you can say that a model precludes a channel precludes another channel. And for example, if you have a wave in a wind farm, you have a wave that is hitting one sensor after another. With a model that takes account of the different delays between the channels, you might be able to predict the wave. Whereas if all the models are correlated instantaneously, there's no point of channels preceding any behavior with respect to one another, and that is possible with the MOSOM kernel, the multi-output spectral mixer, because of the complex valued function that we design. I think I answered all. So.
Yep, I think so too. Sorry, my just cut out. Yeah, if anyone else has any questions on the topic, I guess it makes sense to put them in this the Slack channel, and then there's quite a few people who are, you know,
okay. I didn't know about the Slack channel, but if you want to see this, I can enter and answer a few questions, no problem.